All right, so these notes are for section 4 of chapter 7 in chemistry, and we're going to talk about empirical formulas. Um, these are actually pretty easy to do, though the math looks really ugly and complicated at first. It's actually one of my favorite things to do in chemistry because really ugly numbers turn into really nice, clean answers very quickly, and it's kind of cool. So we got to be able to determine these empirical formulas, understand what that means, and talk about the connection between empirical formulas and molecular formulas. Right? So we'll just jump into some examples, but first, an empirical formula, smallest whole number of ratios and elements in a compound. Remember, when we're talking formulas, if it's an ionic compound like calcium chloride, those two numbers, one calcium, two chlorines, those are already reduced, and they're always reduced. So ionic compounds and empirical formula is the formula, right? Whereas for covalent compounds that possibly could be reduced, because glucose, remember, could be reduced down to one carbon, two hydrogens, one oxygen, right? All sugars reduce down to this form, right? In fact, that's why they're called carbohydrates. But that's the difference. The CH2O is like the empirical formula, whereas glucose actually has 6 carbons, 12 hydrogens, 6 oxygens. And there are other sugars that may have like 7 carbons and 14 hydrogens and 7 oxygens, right? So you got to be able to go back and forth from empirical formulas to real formulas. Otherwise, when you're determining an empirical formula, you're going to be given data like this in percents, and it's pretty simple. It's pretty easy. If you got a percent, you're just going to assume that it's a mass, because we could assume that my total mass of this sample was 100 grams, right? So 36.7 grams of it would be that potassium. And I'm going to start calculating, changing grams into moles. So I just got to look up, potassium is 39.10 on your periodic table. I got to divide there. This would give me 0.9386, it looks like, moles. And then I do the same thing for the chlorine, so 33.27. I'm going to assume that's a gram value. And I'm going to divide by my 35.45 grams per mole. And that's going to give me an answer of 0.9386. Weird, that's the same number, isn't it? And then I'm going to do that same thing for the last one, 30.03 grams. This is oxygen, so I'm going to use 16 grams per mole. And when I divide those two things, this time I'm going to get 1.877. And when it's all said and done, it's not a coincidence that these two numbers are the same, because I'm going to divide by the smallest value that I get. So 0.9386 is the smallest value. And either way, if I'm dividing one or the other, I'm going to get a value of 1. But when I divide by 0.9386 here, I'm going to get something very, very close to a 2, right? And that's the point. When I do this and then do ratios of the mole amounts, I should get a reduced whole number ratio, 1, 1, 2, and that's going to help me build my formula, because there should be 1 potassium, 1 chlorine, and 2 oxygens. So this is my answer. This happens to be potassium chlorite, which we didn't have to memorize chlorite, but it is on your list, so you could check. It is a real thing, right? It has a -1 charge to match up with the +1 charge of potassium. But otherwise, simple process. You just turn grams into moles, or these percents that are basically grams into moles, and then do mole ratios to figure out your whole number ratios. So then I could have this example, same thing, 17.15. This is grams. Carbon is 12 grams per mole. It's 12.01 grams per mole. Divide that, I'm going to get some value, 1.428, right? If I take the 1.44, call it grams. divided by 1.01 for hydrogen, because that's 1 mole of hydrogen, right? I'm going to get 1.426, right? And then I'm going to get 81.41 grams for the fluorine, and that's 19 grams per mole. Dividing those gives me an answer of 4.285. Again, these all look like ugly numbers. 2 of them are very similar. It turns out when I take 1.428 and divide it by 1.426, it comes very, very close to 1, and I'm just going to assume it's a 1, right? So I'm supposed to get whole number answers, so when it's really, really close to something, you just go ahead and write that. This is also going to be a 1, but this, when I divide, is very, very close to a 3. So 113 is my whole number ratio, so I just write a formula. CHF3. This is a carbon with 1 hydrogen and 3 fluorines connected to it. And that should make sense because this totally would have been a legal Lewis structure from a couple chapters ago. This thing would be called trifluoromethane, right? That's something my biochem students know. But again, real compound, empirical formula, pretty easy to come up with. One more example here. This time I actually told you values in grams. It doesn't matter. You do the exact same thing, right? So I told you this 60 grams here, which is just the total of these 3 things. Doesn't matter. Don't need to know it in this case. But 38.43 grams, change that into moles. So I'm going to divide by my value for lead, which is pretty big. Should be 207.2 grams per mole. That's going to give me a value of 0.1855. And then I'm going to take 17.83 grams. And I'm going to divide it by 12.01. And that's going to give me a value of 1.485. And then I'm going to take my 3.74 grams, divide that by 1.01. And that's going to give me a 3.70. Again, nothing looks great yet, no clean numbers. But when I divide by the smallest, in this case, that 0.1855 is the smallest number. So if I divide everything by that value, I hopefully can get some whole numbers. This is a 1, obviously. 1.485 divided by 0.1855 is an 8. Divide that here, and I'm going to get something very, very close to a 20, which is fine, right? That's a big number, but that's what it's going to end up being, because this lead is going to have 8 carbons and 20 hydrogens to go with it. Now this tetraethyl lead up here is actually why fuels now say unleaded, because that used to be found in fuels, right? We used to use that as an additive until we found out it was making us dumber, because lead poisoning is a problem, right? But if I kind of write that differently, it would be recognizable, at least to one of my organic students. Again, biochem, we do different stuff than you guys. But you guys should be able to follow that from what you know. This is my tetra, this is my ethyl, and obviously lead's pretty straightforward. But this is a real compound, definitely my correct formula, so I did that right. And then this one more example here before we jump into the molecular formula versus empirical part of the notes. Right, this one is actually extra. It's not in your notes, so go ahead and put it down at the bottom or something, somewhere where you have some space, because you have to have it, right? You definitely need it. So this has 2 different add-ins to it that you need to understand and be able to follow. So if I started out with this mass, and then I told you that 4.433 grams of that mass was phosphorus, this is essentially my total mass. In this question, I'm going to have to figure out how much of that total was oxygen. So the first step is to just subtract these two things, right? So I'm going to get an answer of 5.717. That's my oxygen. So that's the first step. Sometimes I don't tell you the parts, but you just subtract from the total. You have a missing part here, excuse me, that oxygen. But as long as I told you the phosphorus and the total of the sample, you should be able to figure out what you need to know. Right, so that's complicated, but there is actually one more part of this. It's a little weird. So I get this 4.433, just like we did before. I need to change that into moles. So I'm going to divide by 30.97. And that's going to give me this 0.1431, right? And then my 5.717, I got to divide that by 16 for oxygen. And that's going to give me a value of 0.3573, right? And when I divide by the smallest in this case, something weird's going to happen, right? This is a 1. That's not weird. But when I divide by 0.1431 in this case, I actually get a value that says 2.497. Now that's not very close to a whole number, but it's very close to a half. And the next step to this is sometimes you don't get your whole numbers right away. So if you recognize that that's 2.5, I can get rid of a half easily by doubling this, right? And that turns into a 5, right? But I also have to double this, so that's going to be a 2. So that means my formula is actually P2O5, right? And that's actually correct. This is a diphosphorus pentaoxide. But it can be kind of weird because you're looking for these whole numbers and every once in a while you don't get one. But it should be very, very easy to recognize. And I'm going to give you a whole list of those to recognize so that you can unreduce them, because that's going to be a problem. So 2.5 is not actually close to 3 or 2. It's halfway in between, so I have to do something about that. If I'm going to assume that something's a whole number, it has to be a few hundredths or thousandths away from being that whole number, or it's really not what you think it is. So most of the time you're going to get whole numbers, but you're going to have to learn to recognize a few endings so that you can deal with it. All right, so that's the first half of these notes.